Good evening and welcome. My name is Lisa Lamb. I'm honored to welcome everybody who's joining us this evening. I will serve as the moderator for our post-eclipse symposium tonight. I'm the president CEO for the Lewis Center for Educational Research, and I'm also the lead educator for our GAVR radio astronomy program. So thank you for joining us. I'm sure many people are coming in. Hopefully you were able to join us for our Eclipse broadcast last month. In fact, we had more than 10,000 participants joining us really from all over the world, all across the nation and 6 different countries. And so as an Eclipse team, both student Eclipse ambassadors and professional scientists and engineers in the Eclipse team, of course, we don't want the eclipse to end. That experience was so amazing, and we wanted to come together so that we could share our findings and takeaways and just talk science. So that's our plan for tonight. We are going to start our broadcast by hearing from our student teams. We have 5 amazing student teams who were collecting data and working countless hours, both prior to the eclipse to prepare, during the eclipse, and have been meeting continuously after to analyze their data. So you're going to hear from each of those 5 teams. Each team will come on, they will introduce themselves. They'll tell us which schools they're representing. They've also prepared a short video for us to view that presents their findings, because not all of our students were able to join us tonight. It is AP testing time and a lot of busy season for high schools across America. And so we have a video prepared from each of the teams. But while they're presenting, what we'd really love is if you could ask any questions or put any comments into the Q&A section in GoToWebinar. And then after their video, that team will turn on their cameras and their microphones, and we're going to have them field a couple of questions. We're especially excited for the students who are joining us tonight to be asking questions of other students, as well as any online participant to ask questions from the students. And then, so that's going to be the first portion. The second portion, we have an amazing panel for you of STEM professionals. We are incredibly honored to welcome this amazing crew. The next one, that's us. That's our GAVR team. This team right here. So we have Dr. Steve Levin, Dr. Belu Thangasamy, and Marin Anderson, all joining us from NASA JPL. We have Professor Bob Twiggs, who is an amazing space engineer, co-inventor of the CubeSat and founder of Twiggs Space Lab. And I know many of our students here in California are ecstatic to talk to retired astronaut Dan Tawney. So that's going to be the whole second half. You're going to have also an opportunity to hear their perspective of the eclipse, some takeaways, including data analysis, and then just anecdotal takeaways from the experience, and ask them questions. So to get us started with our first portion, I have the pleasure of introducing my very good friend and colleague, an amazing teacher at Bishop O'Connell High School in Arlington, Virginia, Mrs. Melissa Poore. Melissa? Oh, wait, one more thing. We can't go yet. Also, a certified GAVR teacher. Okay.
Yes. So thank you so much. Yes, I am actually, that's the second thing I wanted to say. So I'm excited to continue my own learning with my students, but also in radio technology, radio astronomy, amateur radio, and all of that. So I'm excited to be here. So let's get going. On the day of totality on April 8th, I was in Meridian, Texas with an incredible mix of students that, you know, I say a mix because collaboration, the virtual feeling was that they were there with us. So I reported live from the field. I was connected with all of you, but more importantly, we were connected with our Eclipse monitors and hardware as a student team of scientists in the field. So we had students as hardware custodians helping monitor in totality for students that were not there. We had people in their communities monitoring, including at my home school in Arlington, Virginia. So we're very proud to bring these results to you and just to bring ourselves along in some new interesting information and data. So just one more thing about that day. You're going to hear some incredible perspectives, but mainly you can't capture what actually happened that day until you hear it out of their voices and see it in the pictures. So in general, we had balloons tethered, we had them going up, we had students live on the ground, and now I want to turn it over to them. I believe I said the important things I wanted to say. So Lisa, we're going over to our first team, I believe.
We are. Of course, it's my distinct honor to introduce the very first team from the Academy for Academic Excellence, a Lewis Center school right here in Apple Valley, California. So let me get out of their way.
All right, good evening, everyone. We're so excited for this opportunity where we get to present this data to you. We're going to go ahead and start off with our introductions. My name is Mosiah Gonzalez, and I'm an AAE student, 11th grade.
Hi, I'm Caprice Kaasi, and I'm an AAE student, 12th grade.
Hi, I'm Natalie Ritter. I'm also in 11th grade, and hope you enjoyed the video that we prepared.
Hi, everybody. We are the Student Solar Eclipse Ambassadors team. We are from the Lewis Center for Educational Research located in Apple Valley, California, and my name is Caprice Kaasi, and I'm currently in 12th grade.
My name is Natalie Ritter, and I'm in 11th grade.
My name is Mosiah Gonzalez, and I'm also in 11th grade.
So for the Eclipse, we had a total of 10 monitors, and we sent 7 over to Meridian, Texas, and we kept 3 of them in Apple Valley, California. We were able to compare the data points because in Texas, they experienced 100% totality versus here in Apple Valley, we experienced only about 60% totality. So once the Eclipse monitors were sent back to California, after the Eclipse, we were able to compare the data sets from the variety of monitors, and we were able to see the different metrics that the monitors acquired. And the 2 that stuck out the most to us were humidity and temperature.
So in regards to temperature, what we found during this experiment was that it followed our hypothesis that Meridian, Texas, as being in totality, would experience a more significant temperature drop. What we found is in Meridian, Texas, they received a drop of 25 degrees Fahrenheit, while us in California received a 18-degree Fahrenheit drop. What we also found in Meridian, Texas was that on top of their original 25-degree Fahrenheit drop is that during totality they received about a 2 to 3 degree drop on top of their 25 overall downshift.
As for humidity, we were very surprised on all of the measurements because we expected the humidity to decrease with the temperature. However, there was almost a direct inverse to the temperature where the temperature dropped, the humidity increased. So in Texas, we had about a 40 percentage point difference between the totality and afterward. And here in California, we had about a 20 percentage point difference.
Something we also noted the significance of was having multiple tools recording data at once, especially during such a significant event as the solar eclipse. While we were recording data in California and Meridian, Texas, we had our Gabbert team using an antenna to take radio data, and our astronomy team taking optical pictures, which gave us a different perspective and insight on such an amazing experience as the solar eclipse phenomenon.
My favorite part about this experience was getting to collaborate with all of the students in Texas and getting to hear their stories and accounts of the totality, and as well as looking at the data and being able to compare it with ours here in California.
Finally, we want to thank our viewers who tuned in with us for the entirety of the event, as well as our Gabbert science team who collaborated with us for the eclipse. We want to thank the ambassadors over in Texas as we lived through them vicariously as they were in totality for the eclipse.
Signing out from California.
I didn't get to know that we were all 3 doing it. Do it again. Do it again. Yeah.
Okay.
The last one where I was like, I didn't know we were all supposed to.
Yeah.
Okay. Do we have any questions? No? We might not have any questions, but I'm pretty sure we shouldn't let them off that easily. Do any of our STEM professionals have questions for this team?
Well, I definitely have one. You called out the humidity variation. Have you figured it out yet?
Like why was it?
Figured out why it did what it did?
Do you know?
Not exactly. We looked kind of into it, but we didn't find a concrete answer to that question yet.
So you might remember during the webinar, in real time when it was happening, and you noticed that and brought it up, Dan and I had a little conversation back and forth about a possible idea. So you might want to follow it up. The idea is if you're measuring relative humidity, then when the air temperature gets colder, it doesn't hold as much water, so the humidity should drop like you expected, but the relative humidity goes up because it's what fraction of the water is in the air that it could hold. So it can't hold as much. If the water doesn't change much, then maybe that's why it went up. So it's just a hypothesis, but that might be a way for you to follow it up and try and figure out if that's what's going on.
Dan, did you want to add anything to that?
No, that was the exact point I was going to make. And if now that you might be able to correlate the temperature data with the humidity data and mess around with the numbers and see if you might be able to get a linear or find out what the relationship is exactly between the temperature and the relative humidity.
I thought that was really interesting. I have to admit, I hadn't thought much about it. And then seeing the data, and it really brought it out, because I thought, is that right? So I went to Google and looked it up. And sure enough, it was interesting. But one thing I would like to do is encourage the students to still have the Eclipse monitors. Go sit them outside overnight, see what happens. Take that data and look at it. It's really fascinating.
Yeah, definitely.
Yes, sir.
Okay, all right. We're gonna do a little switcheroo.
Thank you.
In Gabbard headquarters. They're not going anywhere though, they're just sliding to the side because we are now ready for our second student team. Next, we want to turn it over to the STEM Enhancement in Earth Science, or SEAS team from the University of Texas at Austin. This team had participants from 8 different states. And Raj, you want to go ahead and introduce the team?
All right, can you hear me?
Yes, we can.
Cool. My name is Raj Sinha. I'm a part of the C's Eclipse team. I'm a junior and I go to Lang Creek High School in Houston, Texas. I think Ryan, you here?
Hey, can you guys hear me?
Yep.
My name is Ryan Schaefer. I'm a senior. I attend Lower Merion High School in Philadelphia, Pennsylvania.
All right, we're gonna go ahead and show you guys.
And Ella.
Oh wait, hold on. Can you guys hear me?
Yep. And see you.
Hi, my name's Ella. I'm an 11th grader and I go to the Alabama School for Math and Science.
Okay.
Hi, my name is Anna. I'm a senior at the Stewart School and I'm from Richmond, Virginia.
Alex, are you on?
Yeah, can you hear me? Yes, okay. Hi, I'm Alexander Beckman. I'm a senior at Park Tudor High School in Indianapolis, Indiana.
Okay, now we're gonna watch your guys' video.
Oh,
Oh, wait, did we miss somebody?
yeah. Sorry. Can you guys hear me?
Yep, we can.
Yeah. My name is Nick Mendez. I'm a junior from Caldwell, Idaho, and I go to Caldwell High School. And we all hope that you enjoy our video and see our experience with the Eclipse.
Hi everyone, my name is Raj Sinha and I am a part of the NASA C's Eclipse team. Today we will be presenting our findings and experiences in Austin, Texas during the 2024 total solar eclipse.
Hello, I'm Alexander Beckman. In the summer of 2023, we 8 NASA C's interns were tasked with designing a prototype high-altitude balloon payload for the April 2024 total solar eclipse. We had months of off-site training before spending 2 weeks in person at the Center for Space Research, building, designing, and testing our prototype.
AGU was the National Science and Engineering Convention hosted in San Francisco in last December, and it was where my team presented our project.
During the eclipse, we witnessed many natural phenomena, such as rapid darkness, a 360-degree sunset, and how gravitational waves affect local cloud arrangement. This eclipse also represented the end of our 10-month SEAS experience.
We were able to view the eclipse with students from Allen Academy, who taught us changes to look out for during the eclipse, and we were also able to help them with their experiments.
While setting up for our experiments, as well as throughout the entire eclipse, Ms. Poor was able to document our results and our experiences on the NASA TV live stream, where we were able to answer questions, comment on our observations, and explain our collaboration with the California Eclipse team.
We collaborate with students from California by helping set up their sensors, monitors, and devices throughout the ranch. Not only did this experience teach us the importance of collaboration, but showed us that like-minded students like us are all over the world, and that collaboration can happen through many unexpected ways.
I'm glad I was able to view the total solar eclipse and also capture video to continue studying it.
I'm incredibly grateful for this opportunity and will always remember being 18, surrounded with my friends, and seeing one of the miracles of the universe.
My favorite part about the eclipse was how drastic of a difference there was in brightness just between totality and the moments before and after.
Being able to witness such an impactful event and simultaneously conducting science with amazing researchers and educators is something that I will never forget.
It was a truly special moment to have our work with SEAS come to fruition in perhaps the grandest way possible.
This experience has got me one step closer to achieving my dream of becoming an astronaut.
It was a surreal experience seeing the total eclipse, and most importantly, seeing our hard work and dedication come to fruition.
The eclipse made a direct change on the world and my life.
Thank you, Ms. Miller and Ms. Baggio, for orchestrating these fantastic opportunities, and thank you to Ms. Tomlin for providing us with an incredible space to witness the eclipse.
And a big thank you to Mr. Twiggs for providing the technology necessary to complete our tests. And a big thank you to Mrs. Poor for helping organize our collaboration with the California team and facilitate this awesome trip.
And thank you Lisa Lamb and Ryan Dorsey from the Lewis Center for making the broadcast possible.
All right, awesome work. What a diverse and eclectic team. I think that's just amazing. Do we have some questions from our University of Texas SEAS team?
I do want to say one more member just popped on.
I would like to ask a question about, I think you put some monitors on a tethered balloon. Did you see any difference on the balloon than you did on the ground?
Unfortunately, we couldn't see the data. We had sent the monitors off to California before we got any information, but it was definitely such a really interesting experience seeing the difference really just in the height of the balloon, because our experiment wasn't necessarily there was lots of wind, and so the height of the balloon kind of varied a lot. And we thought it would be interesting to see some of the changes that might happen because of that.
So is the data, do the folks in California have the data? Sounds like
yes,
something
I'm not sure.
To share, right?
Some of the graphs that they showed, I'm not sure if it's from the actual one on the balloon, but I know that they do have the data.
It was from Firecracker, and we will absolutely share the Google Drive with all the Eclipse data with you guys.
Yeah, so that the data
That's a great point.
Was, who was Firecracker? Who had Firecracker? For all of our other participants, the students named the Eclipse monitors. So the example used was Firecracker. There's still, I think that's a great thing about this. We don't want this dialogue to end. So there's still a lot of analysis that we can look at as we pull that data. So I think that's a great one.
Can I point out something? During the procedures and processes involved in development, equipment handling, and all of that, we did have a change of strategy. So our TASER team had their own units in the field in their community, and we had a pre-meeting with them, and we thought they would be the custodian, but that is why our hardware was handled by this Eclipse team. So they were down there and had to get back on a bus, and then I was delivering the hardware back to California. So that will be an exciting follow-up to show them that shared data. That's right.
All right.
Does anyone remember who had Firecracker? So they exchanged personal notes and memorabilia. And does anyone recall, Nick or Raj, do you remember one that you had, and you all wrote notes back, put your first name, right?
Right. I'm not sure who specifically had Firecracker or not.
Right. We had about 8 units, I think.
It's Firecracker because Bob sent the kids the little ducks. And so for anybody who's joining us, all the ducks went to Texas and came back to California. And we very proudly are keeping the little quackers. Little quackers. Come over here, Matt. Come here, show your little quackers. They had a lot of fun too.
I might say that there were really unique objects and containers and holders and platforms that students made out of cardboard, as well as developed design, added color and community to it. So we could see one of them had a really cool Texas and California symbols on it. So that was, if you all recall, it was such an amazing day, overwhelming. We captured in pictures, but yeah, I just want to remind everyone, I saw that happening, and the exchange of hardware was the important thing. They had to make sure they did everything the same, test it, and make it work. And so far, that part was really successful. I don't think either team really knew that yet till now.
Yeah, there were a lot of unintended. So our team's bringing out all of the monitors. Okay. All right, we will stage these. Next, though, we are ready to hear from our SEAS Taser team from Texas and London. I think you're here to represent your team.
Hi, I'm London. I am a junior at James Martin High School in Arlington, Texas. And I'm ready to present our video. The rest of my team couldn't be here tonight, but I'm here to represent for them.
All right, London, let's look at your video.
Good afternoon, everybody. Welcome to the Texas Solar Eclipse Research Presentation. During the April 8th solar eclipse, Professor Bob Twiggs, Melissa Poore, and Laura Tomlin aided our TASER team in collecting atmospheric data to understand the effects such a rare astronomical event has here on Earth. We are very excited to share what we have found, so without further ado, let us begin.
Hello, my name is Haley Gooden, and I'm from Hunt, Texas.
Hi, my name is Victoria Mascoro, and I am from El Paso, Texas.
Hi, my name is Ariel Reyna, and I'm from San Antonio, Texas.
Hi, my name is London Franklin, and I am from Dallas, Texas.
To collect our data, we utilize an Eclipse monitor created by Twiggs Space Lab. The Eclipse monitor contains sensors that measured temperature, humidity, barometric pressure through estimated altitude, and also contained a 3-axis accelerometer. This monitor was on and collecting data for the duration of the solar eclipse. Each person's findings differed, but showed the same overall trends.
Now, to first begin with, the ground team actually experienced temperatures below 80 at a normal range of 60 to 75. As it began to end its polarity, though, the temperature began to climb up again around 90, showing us that the coverage of the moon from the sun was strong enough to lower the temperature back here on Earth, as with humidity being the same and returning to an average of what El Paso and Hunt would sit at. Now, for the HAB team, the balloons actually were focused on altitude to see if the distance from the Earth would help in any new data being collected, and it showed actually that the temperature would cruise around 70 to 80, with not much change after the eclipse. But the humidity for both began to spike down very, very quickly and come back up to reach normal levels of both Dallas and San Antonio would be giving us. But it gave us the opportunity to see that the data temperature was a lot more accurate if on the ground, and humidity would show better results if it was tethered on the balloon.
In conclusion, the temperature experienced a drop of about 10 degrees in each area that was observed. This can be attributed to the moon's position in front of the sun, which blocked the solar rays shining upon Earth. The high-altitude balloon team, or the HAB team, noted a significant change in humidity, including a quick drop during totality and a slow rise as the moon shifted in position. This can be observed because as the temperature dropped, the cooling effect caused the moisture in the air to decline. And as the heat came back when the sun was more visible, it caused the humidity to rise.
Total solar eclipses are rare celestial events that affect various environmental factors on Earth. Through measuring temperature and humidity changes during the eclipse, we gain a better understanding of this extraordinary event and how it influences environmental behaviors on Earth.
Thank you, Professor Bob Twiggs, Miss Selena Miller and Miss Margaret Baggio, Lisa Lamb and Ryan Dorsey, and the Gabbert team.
Great job. Okay, we have questions coming in, I believe. Do we have any from online participants? Okay, panelists, we have questions for London or other students?
So I'm wondering if the other students want to compare notes on, maybe not in real time, but notes on what happened on the ground in the partial eclipse versus the total eclipse and how that differs from the balloon and the wind, how big an effect the wind has. Have you guys been looking at that? You probably haven't had a chance to even compare notes yet with the other people from other places, right?
Just very at the surface level. I think that, and not all of them. So yeah, I do think that that's a great next step. Melissa, you agree?
I wanted to say that anyone could pop on, the other groups, like students could pop on and ask a question, but in the field, the Eclipse team, we felt winds. So any of you that weren't able to have a chance to speak and you want to ask a question of London or answer in, this is about talking about our data. So yeah, I think when we were reporting from the field, that was one of the significant things, that when we went out, because of the coverage, you know, was spotty during the eclipse because everyone was on the networks, and then it popped back on. We couldn't get over the change in sound, feeling, temperature drop. I think everyone's saying it. So I'm hoping the students will start sharing part of that, because the physical observations on all of that are a whole nother layer on what we are reading in our data. And that's something that we're talking about as we're planning this. We couldn't wait to see how the students would start to envision, oh, well, I saw this, but in California, I saw this. How does it match up? So the speakers that we're going to hear, the way this is unfolding is really cool. So London, you know, do you have a question for them about your data and what you saw?
I do have a question. So I was in the path of totality, but I only experienced a 10-degree drop. Then some of the other teams were in Meridian, Texas, and they experienced a 25-degree drop. So I thought that was really like a difference. It was definitely interesting to see that they had 15 degrees lower than what we got, because we thought 10 degrees was massive, but 25 degrees is definitely a difference. So I was wondering what that could be. Maybe it's I don't know exactly where Meridian, Texas is in relation to the Dallas area, but I do know that day Dallas, it was really hot. So it was probably because it was so hot, and it could also depend on the clouds. We did not have too many clouds that day, so there was nothing to help bring the temperature down. I was wondering if in Meridian, did you guys see clouds? Was it really hot when you began? What did it feel like? And Nick?
Yeah, so I could definitely answer in response to that. So when we were in Meridian, Texas, I remember that morning, it was very like little light rain. But once we actually got to the ranch in Meridian, after traveling to Austin, it was hot. You felt the heat, you felt the sun. So I kind of felt that maybe during while the moon was crossing over the sun, the temperature could have dropped way more dramatically, in the sense that the following day, I traveled to Dallas, Texas on my way back to Caldwell, Idaho. And over there, I remember it was really rainy and really cold. So I kind of feel like there might have not been that much of a variation when the moon covered up the sun. So I feel like that kind of could go along with just how there wasn't as much of a dramatic drop in temperature as there might have been in Meridian, Texas, where it was really, really sunny, compared to Dallas, where I felt that it was more like rainy and cold.
That would make sense
Get
because
the-
one of the things that we also attributed the heat to might have been humidity. And we did get a lot of rain that week. So it could be one of those things that I know the humidity has to do with the temperature, but since the temperature didn't drop that much, then the humid particles in the air didn't go away as much. So that's a very good observation.
So you guys sound like you've got a pretty good idea there. I might one other thing in the mix for you to think about, which is when you see the temperature of the air change, whether that's the temperature of the air itself is changing there, or colder or warmer air is coming in on the wind from up above or down below. So you might want to add that into the mix as you're thinking about all of this. It sounds like you got a really good idea about what's going on here.
Yeah, that's a good idea. I was also gonna, I was thinking there might be an effect of, were you standing on the pavement, or and were other groups standing on grass? You can imagine feedback from, if you were standing on a street or a pavement, would be greater than if you were standing in the field or you know, not on, or you know, I guess grass or something like a field.
We did, well, me personally in Dallas, some of my other teammates were also on concrete, but we were definitely on concrete. And I know the Meridian, were you guys on grass?
Yeah, I was gonna mention that at least where I put the sensor that I received, I put that one on grass, but I know a few of the other ones are placed on dirt and in trees.
That makes sense.
So I've been having an idea. I'll just bring it up while we're talking about it. You can do your own. We can start doing your own mini eclipse experiments at different scales. You can use an umbrella, right, and create your own little eclipse with an umbrella, or even a piece of cardboard, or you could use a big carport. And so you can sort of kind of scale different eclipses and see if there's see what effects you can see from those too. Because if it's just blocking the sun, now maybe you can start eliminating other independent variables like standing on concrete, standing on grass, wind, no wind, stuff like that.
Mm-hmm.
We do have a couple.
And don't forget how wet the ground is too, because water holds a lot of heat.
Oh yeah.
Okay, we've got a couple of questions from the online participants.
One question was there something that was particularly surprising when working with balloons in the field?
Oh, I can answer this. I did a high altitude balloon, and also Errol did a high altitude balloon. She had, with altitude, her humidity differed, and she also noticed that the data you received back wasn't as quantifiable as the data that was grounded. So I put a desk cube thingy into my balloon, and then I grounded the Eclipse payload, but she sent the Eclipse payload up. So her Eclipse payload data compared to my Eclipse payload data differed a lot in our humidity because of altitude. So if she said if she could do it again, she would keep it grounded.
Interesting.
Okay, next team. Okay, we are going to take it to our next team, and then if we have more questions, keep them coming in the chat. You should see on the panel and go to, if you put the arrow, click that top arrow, it should expand and you should see a section to enter questions there online. But let's take it to our team from Bishop O'Connell High School in Arlington, Virginia. Ella, I believe you're going to get us started.
Hi, my name is Ella. I'm a sophomore at Bishop O'Connell High School, which is in Arlington, Virginia, which means like our data was not in the path of totality, so it's interesting to see the difference between them.
Hi, I'm Ashley. I'm also in 10th grade at Bishop O'Connell High School, and yeah.
Okay.
Hi, I'm Catherine. I'm in 9th grade at Bishop O'Connell High School.
We ready?
Are we ready? All right, let's roll it.
On the edge of shadow, Weather effects of the eclipse from Arlington, Virginia, which is a region that is not in full totality. In our area, maximum reached up to 87%. Before we begin, an important thing to understand is that all data is not perfect. For example, the eclipse monitor was turned on before it was outside in the collection area, giving a portion that is briefly above, which is considered bad data. However, the rest of the reading is still valid. Altitude is a constant, meaning it stayed the same throughout the trial, since we did not move the eclipse monitor. It helps to confirm that the data was actually valid and that things were working as they should. The graph for humidity and temperature represented an inverse relationship, meaning that as temperature goes up, humidity went down, and vice versa. The overall trend in the data was decreasing, which makes sense because the moon slowly covers the sun, which is a source of heat, so it made everything slightly colder. The strange thing about the data is that there's a spike in the temperature before coming back to the overall decline. By graphing seconds on the x-axis, we determined that the spike occurred right before solar maximum. We have come with two possibilities. Possibility number one is a solar flare. A solar flare is a strong burst of radiation that occurs when a sunspot is active. Solar flares can briefly increase the temperature, which could have explained the spike in the data. Possibility number two relates to lenses. During totality, a shadow is focused to a certain point on the globe. I noticed that seems very similar to how a convex lens works, focusing light to a certain point. My theory suggests that the moon works like a convex parabolic mirror, which is a fancy term but essentially means that the moon is in the correct position right before totality that would make the light reflect sort of like a glare of a mirror when you put it at a certain angle. Out of two possibilities, a solar flare is a little bit more likely, but no one has really figured out which one is correct. To end, I would just like to give a special thank you to Professor Bob Twiggs, who helped us figure out how to graph the data and think critically about it, without whom this presentation would not be possible. I would also like to thank Lisa Lam and Ryan Dorsey for setting up a live broadcast for us to showcase our work. And I would like to also thank Ms. Swaim, who let us get out of class for Eclipse data collections. And last but not least, I would like to thank Mrs. Poor, who helped us conduct the experiment and overall the whole entire process. So thank you to all of them.
That's very interesting data.
We did have a question from the professor himself. Professor Bob Twiggs would like, what other data would you like to measure with the Eclipse monitor?
Oh.
Annalena, if you're on, turn your camera on.
I don't know why it is.
I think, I think maybe like a function for like that could detect radio waves might be helpful because like a solar flare also releases like gravitational waves, and if there was some kind of like radio function, it might have been able to pick up on that. So yeah.
Okay. We're going to keep moving because, of course, we all love this and could talk forever, but we want to make sure that we hear from our next student team and have time for our professional panels. So next, we're going to move to our team from Harmony School of Innovation in Waco, Texas. Abdiel?
Hi.
Hi.
All right. Well, like I said, I am Jorge Abdiel Comona Trejo. I am a sophomore at Harmony School of Innovation, and I am here in Waco, Texas.
Let's watch your video.
Hi, I am Jorge Carmona Trejo from the Harmony School of Innovation here in Waco, Texas, and I'm here to describe my experience with the solar eclipse. As you can see in the pictures here, the solar eclipse was, well, we observed the solar eclipse in my front yard. and we could see a bunch of pictures that were taken, including one where the sun was going through a tree, and the little bit of sun that went through had the cover and the moon. So we could see how much sunlight was left and how much the moon was covering it. And the other two, the bottom left picture shows a picture taken from a camera that was almost just so close to totality, but not there yet. Then on the one on the right was a picture of totality being covered by some clouds. Here you can see it's me and my family, and you can even see the camera that was used to take the pictures. It was just a regular camera that we cut out a lens for and put on top so you can see it. As you can notice on the left, the picture's a little bit darker, and that's because it was taken just before totality, which is when the lights went away, and when we also saw diffractions going through the wind, you could be seen on the floor, and the birds started to roost and thinking it was nighttime. And when totality was over, we saw the birds fly away, and the light came back a lot faster this time around. Now the picture on the top right is a seminar we went to just know how the whole event happened, what happens in the exact science behind it. And we saw they showed us the path of totality and just a bunch of cool stuff that we learned about that helped us just know what an eclipse is. Now what the solar eclipse monitor got was two different things, two main things, temperature and humidity. As you can see, temperature, there was a spike in the beginning because I put it on some concrete in the sunlight. So it heated up a bit and it went up. Then the divot or the dip was when totality occurred. So when it went down, and then it went back up as the sun came back. And then it started going down because we were expecting a storm soon. The same can be seen in humidity. It started out high, it was left in the sun, so it went down. Then totality happened and it went up. Then it went back down. Then it started going back up because of, again, the storm. Now, I'd like to say thanks to my parents, my teachers at HSI or Harmony School of Innovation, and Ms. Judy York for just giving me the opportunity to do such an awesome project.
That was awesome. Okay.
That's wonderful. Very nice.
Questions for Abdiel? If we have some coming in offline, or any of our panelists or students.
Let's see. A question of what caused the wind during the eclipse?
Okay, so one thing that my dad told me is that whenever there's a certain peak when it's about to be the totality, the sun has this form that makes it where you can see the wind currents, the fractions, I think it's called, and basically is when the sun would hit at a certain angle, you can see the current of the wind or how it changed and how it would move on the floor. And we saw that for a few seconds before totality and a few seconds after totality.
That's very cool. Okay. All right.
Can I, sorry. I was going to say something that a previous group mentioned about a solar flare. I remember them saying there was a spike that could have been by a solar flare, and I can say that during the totality, or just a little bit before, we were noticing a little red smidge that was coming out of the moon's covering of the sun. And I investigated a little more into that, and it turns out that it was a solar flare. So a solar flare would totally be a viable answer to their question.
Okay, terrific. Okay, thank you to all of our amazing Student Eclipse ambassadors who were able to join us online tonight. Don't go anywhere, we're not done, but just thank you, you guys, and even for your teammates who had other obligations and couldn't log on tonight. I want you to know that we prepared certificates of recognition for each and every student Eclipse ambassador. Mrs. Poor and I will make sure that those are delivered to your schools and that you receive them. Please share them with your teachers and your administrators and your parents, because we're very proud of the work that you've done. All of you have given a lot of hours on top of everything else you're doing in your schools to contribute to this science, and we just couldn't be more proud of you. All your work is commendable, and I think that everybody, I'm getting texts, if you guys see me looking down, it's because other people who are participating all across the country, including my sister in Orlando, Florida, are sending texts about how amazing you are and how impressed and articulate you are. So we are very proud of you. So, but it is time to transition from you guys to our esteemed panel. So just as with our students, please place your questions into the question box on the GoToWebinar. And we are going to start with this young man right here. This is just somebody I have had the absolute pleasure and honor of getting to know through this process, and I hope that we have plenty of collaboration ahead of us. He is a true pioneer in space engineering. He's the co-inventor of CubeSats, which you know has revolutionized the entire space industry. And he is the founder of Twiggs Space Lab, our beloved Professor Bob Twiggs. Bob, talk to us about what you see as coming next.
Well, you know, thank you for, and all of the students for doing this. I had no idea that it would turn out as good as it did. And I thank you for all of your effort. And what we would like to follow up here with as soon as we can is to tell you what more you can do with the Eclipse monitor. Those that didn't get to keep the Eclipse monitor, let Lisa or let Melissa Poor know, and we might be able to make arrangements for you to get one of those back. And I'm having so much fun with mine now. I've made some changes to it, so I take it and set it out every night and then collect the data the next day, and I'm seeing some really fun things. We get some really nasty storms through Texas here, and I'm waiting to want to add some additional instruments on it to find out more about it. That I'd like it to see what else is going on during these nasty thunderstorms we got. But it's fun to look at that data, and I hope I can get some feedback from all of you on, again, what did you like about the Eclipse monitor? What can we do to make it better? Because there is so much stuff out there that we can measure. And to tell you the truth, I've never measured it like this before. So this is new and fun for me. So thank you for letting me play with you. My goodness. And I think the other professionals here might say the same thing. It's so exciting to see the students learn. Thank you.
Absolutely.
Yeah.
I might.
Okay, I think we're all on Team Bob. Do we have questions for Professor Twiggs coming through?
I would certainly concur with Bob that these are fantastic data set, the enthusiasm of the students. And to be honest, I haven't seen any of this data myself, how the temperature and the humidity is changing with the eclipse, you know.
Well,
So,
maybe we'll have to send you an Eclipse monitor. Would you be willing to play with it?
it is amazing, you know, I'm sure it will be fun.
Yes. Okay. Well, I think we ought to just,
we'll give one to Bailey and
to you and the students, and fantastic, and it is wonderful.
Bob,
thank
we
you.
did get a question from online. Do you think the use of monitors paves the way for students to conduct their own personal studies in order to become more involved with NASA and space in general? If so, what would you like to see in upcoming generations utilizing this resource?
So I have a comment, but I think that question was meant for Bob, right?
Yeah, Bob, and then Steve, you can add on. It's a great question.
I'm sorry, ask that again, would you?
Yeah, do you think that the use of monitors, Eclipse monitors, paves the way for students to conduct their own personal studies in order to become more involved with NASA and space in general?
Absolutely. Absolutely. It's really fun, you know, to have something that's actually measuring it. You can't get your, you know, your temperature gauge and your humidity meter and sit down and record it like that. So it's really interesting to go on. And these instruments are not infallible. You know, you get bad data with them, and that's a real thing in real instruments. So it's kind of fun. Oh, well, I got a funny glimpse in it. And so I went down and I deleted that data point, and then looked at it, and it made a whole lot of difference. So to me, it's a lot of fun. I just love we built satellites, sent them into space, been there, done that. But it's really fun to take data and around your community. So that's where I would like to do more things, is have instruments that measure what's going on in your community. Do you ever measure what the pollution is like near your school? When that traffic comes by in the morning. So there's so many fun things that we can do. I hope I get a chance to work more with you and we make more of these things available to the students.
I think that's our collective commitment. Okay, we are going to transition. Sorry, Steve, we're going to transition because Dr. Marin Anderson, we don't have her for very much longer on this broadcast. So she has some very exciting findings. Let me introduce first two of our Gabbard scientists from JPL. These two amazing individuals, Velu Thangasamy and Marin Anderson, are leading up our Gabbard Solar Patrol campaign. And during the eclipse, Dr. Thangasamy was here in Gabbard headquarters in California collecting radio data using our Gabbard antenna, DSS 28. And Dr. Marin Anderson was actually our field correspondent, official field correspondent for Gabbard, and she was there in Waco, Texas. So we are very excited to learn more about the data that you collected and a little bit about why radio data was interesting during the eclipse.
Yeah, thanks so much, Lisa. I'm really excited to be here talking to you guys. I wasn't doing any science when I was in the path of totality. I was just in Austin in Texas having a good time talking to all of you that were on the Eclipse webinar broadcast about the science of eclipses and the science of radio telescopes. It was all of our Eclipse student ambassadors that you just heard from that were doing science with their Eclipse monitors out in the field. And then, of course, Velu, Nancy, and Ryan, who were taking data with our actual Gabbard radio telescope during the eclipse. But I get the fun job of explaining to you guys now all the cool stuff that they did during those observations and why. So maybe I'll just give some context about the radio telescope that we're using and why, what's interesting, and what we actually why we cared about observing the sun during an eclipse with our radio telescope. So for those of you who aren't familiar, Gabbard stands for Goldstone Apple Valley Radio Telescope. It's a 34-meter radio dish that was previously part of something called the Deep Space Network. And if you're not aware, the Deep Space Network, or DSN for short, is the way that NASA communicates with spacecraft. Anything further out in space than the moon and beyond, the only way that those spacecraft can communicate with us back on Earth, receive commands from us on Earth on where to point, what to do, and the only way it can transmit its data back to us on Earth is through this Deep Space Network. And it's essentially 3 facilities that are spaced out across the Earth that have at each of those facilities a collection of radio telescopes. And these facilities are located in California, in Goldstone, in Australia, outside Canberra, and in Spain, just outside Madrid. And these 3 stations are spaced very strategically around the Earth, such that any spacecraft, no matter where it is in space, when it looks back at Earth to receive instructions or transmit back its data that it's collected, it will see at least one of these Deep Space Network stations. So the really special thing is that our Gabbard radio telescope is actually located at the Goldstone Deep Space Communications Complex. It used to be part of the Deep Space Network. It used to communicate with spacecraft, but we fondly call it retired now. And now that it's retired, it gets to do all the really fun stuff, which is the science that we've been doing with all of you, with the sun, and with many other astronomical objects. So to get into talking about the sun, now that we know what our Gabbard radio telescope is, what I'm showing here is kind of a cartoon onion layer of the sun. We have up in the upper left what we call the photosphere of the sun, which we can think of sort of as like the surface of the sun. It's where almost all of the light that we see with our own eyes, it comes from that surface layer. It comes out of the surface layer of that sun, of the sun on the photosphere. The next layer up into the sun's atmosphere is something called the chromosphere, which you can see depicted on the top right there. And then on the bottom, we have the outer atmosphere of the sun, or what we call the corona. And for the purposes of the radio observations that we're going to talk about today, this is the really important part of the sun. The corona is where we get much of the radio emission that we're detecting with Gabbert comes from, and it's associated with the really strong magnetic fields that are in the corona of the sun. So one really nifty feature about the sun is that as you go further out into the atmosphere of the sun, it actually gets a lot hotter. And that might be surprising because it goes against almost all of our everyday experiences, where if you were, imagine you're sitting in front of a bonfire and you're camping out in the woods and you've got a big bonfire going. The closer that you get to the bonfire, the hotter it gets. And you would think, based on that experience, the closer that you get to the surface of the sun, the hotter that it gets. But it's actually the reverse. So as the further out you get in the atmosphere of the sun, it gets much hotter. Scientists are still trying to understand why exactly that is the case, but we think essentially the answer has to do with magnetic fields. So the sun has really strong magnetic fields looping through that outer atmosphere, connecting back down into the surface, into the photosphere of the sun, and it produces really bright radio emission. And that's the radio emission that we're detecting with Gabbert. All right, we can go to the next slide. So this is an image which is actually taken not at radio wavelengths. This is an image of the sun that was taken with the spacecraft at extreme ultraviolet wavelengths. But I wanted to show this picture because I thought it gave a really nice view of the corona, of active regions, and also the magnetic field of the sun. So this is a zoomed in view of the limb of the sun. What you're seeing here are 3 really bright regions in the corona of the sun, and those are what we call solar active regions. So these are regions of really strong, intense magnetic field in the corona of the sun, in the outer atmosphere of the sun. And you can actually see these magnetic fields in this image. They're represented by that looping structure that you see affiliated with each of those 3 bright spots. And what creates that looping structure is really hot plasma. So really hot electrons and particles that are in the atmosphere of the sun are heated to really high temperatures, and they're confined along the magnetic field in the solar atmosphere. So those looping structures that you actually can see with your eye, that's really hot material in the outer atmosphere of the sun that's following the magnetic field lines. So each of those loops actually represents a magnetic field line in the sun. So these are the kinds of structures that we're actually targeting with our radio observations. And the reason why we wanted to observe during the eclipse in particular is illustrated in the movie on the next slide. So what we did during the eclipse is we pointed our Gabbert radio telescope at a particular active region on the surface or in the outer atmosphere of the sun. And we monitored that active region as the moon's limb passed in front of it. And we continue to monitor it as the moon's limb passed away from it. And if we can play this movie, it'll show that as the moon's limb passes between us and that active region on the sun, the amount of counts that we receive in our radio telescope, so the amount of radio photons that our radio telescope is receiving, it goes down because more and more of that active region is getting covered up by the moon. And so we're getting fewer and fewer radio photons. And then as the moon's limb moves away, as the eclipse starts to end, we get more and more radio flux, more and more radio photons from that active region. And the counts that we get in our radio telescope goes back up. So very similar to what the student eclipse ambassadors were seeing with their temperature data, for instance, where during the eclipse, they were receiving fewer and fewer photons. And so they got lower and lower temperature readings because there was less solar flux heating their eclipse monitors. Sort of in the same way, we got fewer and fewer radio photons. And so what we measured with our radio telescope was declining during the eclipse and then went back up as the eclipse was ending. So if we go to the next slide. Next one. All right, so here's some actual data that we took with our radio telescope during the eclipse. On the left, you can see an image of the sun that was taken during the period of ingress when the moon's limb was moving in front of the sun. And then in the lower left, an image of the sun taken with Gabbert during the process of egress as the moon's limb was moving away from the sun as the eclipse was ending. And for comparison's sake, on the right is an image taken at optical wavelengths with the Big Bear Observatory. This is an optical telescope located pretty near to where our Gabbert radio telescope is located. And you can see the equivalent optical view as compared to the radio view on the left at about the same time. So you'll see a very similar crescent sun structure. You see the moon taking a bite out of the sun in both images in much the same way. And you can actually see the active region that we were monitoring during our eclipse observations. That's AR 13633. You can see it in both the radio images on the left, and you can see it in the optical images on the right. Now on the left, it appears as a bit of a brighter structure, kind of on the left side of the sun. And then on the right, in the optical image, it actually appears as a dark patch. So it appears not as bright as the surrounding parts of the sun in the optical data. If we go to the next slide. Okay, great. So as I mentioned, we're interested in viewing those active regions during the eclipse. And the key reason for that is because it gives us really great high angular resolution data. And what that means is that it's giving us a clearer view of the structure of the magnetic field in those active regions that we otherwise would not be able to access if we were just observing the sun during normal conditions. And the analogy that I like to use for that is that if you had really bad angular resolution, if you had poor angular resolution, it would kind of be like if you were looking at a street sign, but the sign was too far away, so you couldn't make out the words, you couldn't read what the sign said. You could just tell that that looks like a street sign, there's words on it, but I can't read what it says. If you were to somehow improve the angular resolution of your sight, maybe you were to put on some glasses or to put on a pair of binoculars, improving your angular resolution would mean that suddenly you could read the street sign. You'd be able to see what word it said, you'd be able to see the crispness of the lines, and everything would become really clear. And that's essentially what happened for us with our radio telescope during the eclipse. The process of the moon's limb covering up the active region as a function of time gave us really high angular resolution on the structure of the magnetic field in the corona. And the data that we're showing here, these are what we call eclipse curves. So these are measurements of the radio counts, the number of radio photons our telescope was receiving from active region 13633 during the eclipse. And this was during the process of ingress or immersion. So you can see our radio counts are pretty steady towards the left sides of the plot, and then it steeply drops and goes down, and that's due to the process of ingress as the moon's limb is covering up more and more of the emission from the active region, and then it eventually falls down to almost zero, where we're no longer seeing any flux from our active region. If we go to the next slide, we see something very similar. So we're seeing no longer immersion, but we're seeing eclipse curves from immersion or egress. So the moon's limb is leaving the active region, the eclipse is ending, and we are going from nearly zero counts from our radio telescope. There we go. We're seeing nearly zero counts from our radio telescope, and then suddenly the active region is visible again. So we're seeing more and more radio photons from our active region until we get back to the peak of the emission that we would typically see when the moon's not covering the active region at all. So if we go to the next slide. Yes, so as I mentioned, we're getting really good high angular resolution information. The key here is that it's in the region perpendicular to the moon's limb. So along the direction that the moon is traveling is the direction in which we get those really crisp lines. We can make out all the structure in the active region and the structure in the magnetic fields. It just so happens, due to the fortune of the geometry of the Earth-Moon-Sun system during processes of ingress and egress, that we actually have high resolution information in two almost perpendicular directions. So during ingress, we have really good information on the structure of the magnetic fields along that upward pointing arrow. And then during egress, as the eclipse is ending, we have really good angular resolution information along that egress arrow pointing to the left. And I'll just emphasize here that because we were taking data at multiple frequencies, it means we have measurements of multiple magnetic field strengths, and we're therefore probing a vast range of heights in the corona. So we're probing the corona at very low heights in the solar atmosphere up to really far heights in the atmosphere. And this is my last slide that I have to show. This was prepared by Dr. Velu, who has been analyzing our Gabbard eclipse data. And this slide is really meant to just show you that we got some really good data. Our eclipse observations were successful, and we've been able to turn our eclipse curves that I was just describing to you into actual plots of what we think the structure of the magnetic field looks like in that particular active region 13633. And what I'm showing on these plots here are different lines that are color-coded to different frequency bands, or different color bands, you could say. And they're showing you what the structure of the magnetic field essentially looks like as a function of direction along that active region. Again, in those two ingress and egress directions that I described. So our eclipse data looks really great. Big thanks to Belu and Nancy and Ryan for collecting the data during the actual eclipse. This was really important data that we were given a NASA grant to collect, and we will continue to reduce these data and try to learn more about active regions and the corona of the sun.
Okay, yeah. I might just add that you notice there are four frequency bands we have, 3.5 gigahertz to 13 gigahertz. You can look at this looking at different wavelengths. Light, you are more familiar with the wavelengths. So 3.5 gigahertz corresponds to 10 centimeter wavelength. And the 13 gigahertz will correspond to a 2 centimeter wavelength. So this is very important because the emission we are looking at is basically the electrons gyrating in the magnetic fields result in this kind of emission. That means the long wavelengths require low magnetic field. That means, the red curve you see, or the high peak one, that is the long wavelength. That requires 200 Gauss, 200 to 300 Gauss. Gauss is the strength of the magnetic field. On the Earth, it is about 0.5 to 1 Gauss, can say. So it is that. So whereas at the 2 centimeter, which is at the right at the bottom, that is about 1,000 Gauss. It's almost 5 times stronger magnetic field. And it is closer to the surface of the sun. So this is basically the reason why we are doing this. And then the curve, the profile itself tells us how the magnetic field is changing from point to point because of the sunspots. Okay, so this, we are making the measurement above the sunspot. The top figure tells you the magnetic field on the surface of the sun. The radio data gives us the magnetic field above the surface in the corona. That is the reason why we are doing this. And we got a fantastic data. This is still preliminary. I'm sure it will look a lot better when we clean up the data better.
I also want to add something which I think Marin meant to say, but I don't know if you said it, which was that the reason we get the sharper image when the moon comes across is that no matter how blurry the image is from our radio telescope, the edge of the moon is really sharp. By knowing when the sharp edge of the moon came across the sunspot, we're cutting across it with something that's got this really nice sharp line, and that's why we get much better resolution and can get a sharper image. It's because the edge of the moon is sharp.
Yeah, that's right. And that's a really nice feature of observing during the eclipse. Usually the angular resolution of your telescope is a function of the wavelength at which you're observing. So the longer your wavelength, the worse your angular resolution, the blurrier things are. But as Steve said, the moon's edge is really sharp, and it's really sharp no matter what wavelength you're observing at. So you get really good angular resolution for the entire observing band that Gabbert uses.
Okay, we're going to proceed through. We do have two more panelists, but I know many of us probably could have just joined for our next panelist. We are just incredibly honored to welcome retired astronaut Dan Tawney. Dan's flown on 2 space missions, as his bio shows there. He holds the distinction for having performed the 100th spacewalk on the International Space Station and spent a near total of 132 days in space. And he's here to talk to us tonight. And we are just so honored. During the eclipse, if you guys were on with us here in California, we weren't even close to the path of totality, but Dan and his son, John, took us on a ride. We lived vicariously through them, play-by-play the whole time. It was so amazing. All of our students, we had 70 some odd classrooms throughout the Lewis Center joining you and John on that experience. It was once in a lifetime to us. So we're just really excited to hear from you and your experience.
Well, thanks. I'll make it quick. It's just a quick trip report. when I got invited to participate in this science gathering months before, I couldn't because I had an appointment on Eclipse Day. But then a few days before the eclipse, that appointment got moved, and so my weekend freed, or the date freed up, and my son and I made a flash decision the night before to go see totality. So we drove. Why don't you go to the next slide? We drove about 6 hours to our west, and we went to the shores of Lake Erie and we just took the totality map and tried to figure out where we thought the best place would be, and we were looking at cloud maps and everything. And so we ended up in Connaught, I guess. I don't know how to pronounce it, but it sounded like a great place. And my son said, "Hey, there's a beach that we can go and see it on the shore of Lake Erie." So that's where we headed. Next slide, please. So this was using the panoramic, feature on the phone. This is our view. We're up on a bluff, probably, I don't know, 40 or 50 feet above the beach. It's funny that there are beaches on the shores of lakes, but the Great Lakes have beaches. And so this was our perch, and we waited for a couple hours. It was really fun. People were out playing Frisbee and having their dogs running around. It was a real festive environment. Okay, and so we just sat, and here's a guy who had a telescope standing right next to us. And what was really cool is he was able to just project the image onto a piece of notebook paper, and so we could watch the levels of totality as it was coming. So that was a really nice thing for him to do, to share with everybody around the view, because we got in the car and with almost no preparation. We didn't bring cameras. We didn't bring. We had to go buy the glasses. Everybody was given away until, of course, the day before, and then you had to go buy them. So we were relatively unprepared. Next slide. Oh.
Maybe it's the slide before.
No, it should be next slide. Should be another slide.
Oh, it might have gotten missed.
Okay. Well, so do we have? Okay. Well, I had a couple slides showing the view a half hour before the totality, 2 minutes before the totality, which doesn't look a lot different than 30 minutes before totality, and then the moment of totality. So it was nice to have the 360-degree sunset. It was quite stunning, and I didn't have any intentional data taking equipment with me. I just had my skin and my eyes, and so I'm glad that people got to hear my experience, because it's the only record I have of it also, besides the photographs. I didn't make a graph, but I do have one scientific observation about solar eclipses, totality, or solar eclipses. Basically, if you can imagine the totality peaking up here, and what I've noticed is traffic jams they rise very quickly after totality. So there's a very distinct one-to-one relationship between solar eclipse totality, and traffic. So I think that warrants a lot of research. We have to really look into that, figure that out.
You experienced, that was a lived experience. Okay, do we have, I know we are running a little bit late, but do we have questions?
We have various questions that I think are suited to the whole panel when we get to the end.
So let's maybe go to Steve, and then we'll field some questions open to whoever can answer them. So last but certainly not least, it is always our honor to introduce Dr. Steve Levin. Dr. Levin works at JPL. He is the project scientist for the Juno mission, which is currently orbiting Jupiter right now. He's also the lead scientist for Gabbert. And so Dr. Levin's going to share some insight into the importance of this scientific collaboration we've been talking about, and also the benefits of all of you joining our Gabbert team.
All right, thanks. I'll try to be really quick because I want to have lots of time for questions too. I just want to point out two things. One is that this whole process that we've just done today and that we did on Eclipse Day and that I hope we will continue to do parallels the process we do on big professional missions and science collaborations. And that's not an accident because collaboration is the heart of how you do big things. You know, people know of NASA as really good at lots of really interesting things, and JPL, our motto is dare mighty things. We try to do really big projects. The way you do that is with teams. What we have to be really good at is teamwork and collaboration. So you guys have shown the value of that, and I hope you will continue to work with that and do the collaboration as you continue using the data now that you've collected it and started to take a look at it. And for example, you've got a couple of hypotheses we saw. People had things they saw in the data, had some ideas about what might be causing it. Well, the next step, after you've shared that with your colleagues and gotten ideas and written down all the things that you might do, is to do the math, right? Go take those ideas and actually see whether they work. So the flare from the sun idea, go figure out how bright is a flare from the sun, and is that enough to cause that temperature? Or maybe you decide you need to collect more data and you go out and you collect data when it's not an eclipse and see how much things vary and so forth. So I want to encourage you to continue collaboration and to know that the way you're going to do great things in the future is going to be by working in teams. Almost certainly, if you pick any achievement and say, how did that happen? There's a team behind it. Which of course leads me nicely into asking people to join our team. So we have two quick slides, basically for professional scientists and for everybody else. And they're the same basic idea is we want you to work with us. And if you already have a science background or can help mentor, you're an engineer or a scientist, or you just already know a lot about something and you want to help work with the students, we're looking for ways for people to use the data we collect from Gabbard and do things, and to work with our students who are doing things, and with the general public who's doing Gabbard and using the radio telescope. We want you to work with us. We want to work with you. And there's how to connect. And then if you look at the next slide, it's more or less the same thing, but now we're talking about whether you have any prior knowledge or not. If you're a student or a teacher, or just you're interested in this and you want to help, we have things you can do to help. The basic idea is we have this big 34-meter radio telescope, and we want to share it with the world, and we want people to help use it, both running the radio telescope and analyzing the data and coming up with ideas for the next measurements to make and forming collaborations like this. We need people on our team, and we're hoping some of the people hearing this, some of the people who've been part of this, will want to keep going and work with us. That's the part I wanted to say about collaborating and teaming, and invite everybody to join us.
Right. Do we have general questions for our panel at large? We do.
Yeah. Let's see.
And
sorry,
Dr. Anderson, I think that you may need to.
I do need to drop off. I just want to say that it's been really exciting to listen to all of you, especially the students, hear about all of the work that they've been doing with their eclipse monitors and their experience of the eclipse, whether they were in totality or outside of totality. I'm really excited to see what comes next. Thank you all for this opportunity to be here.
Thank you, Marianne.
Cool.
Thanks, Marianne.
I'll say goodbye.
Thanks for working with us.
All right.
All right. So we have a question from online. What sparked this idea to collaborate?
That's a good one. Actually, I think that's for the teachers in the house. And Bob. Melissa, you want to take that one?
I just want to say that the students sparked it, and that Bob and Lisa and I and all of you ran with the spark, and it just takes that little bit to get a ripple going. Bob, do you want to add to it?
You know, this is really fun. The thing that I like to do, of course, is the electronics and the measurement end of it. And you know, I I put this thing together and did not anticipate that it would have the use that it did. So it's really fun, and I really want feedback to tell me more things to do, because I did not realize we had similar instruments, but no way to record the data on them. And boy, you record the data and then you plot it out and look at it, and you say, whoa, that's nothing like looking at, you know, data full time on a display. So it's amazing to me, and let's do some more of this. Let's get more students involved. And you know, how did we affect those students that we just seen? I think it's something that you really can't do any other way, and it's gonna change their lives, and how exciting that is.
Okay.
We have another question from another one of our Eclipse Monitor students. What is something that data will allow us to do in the future?
Like data at large, any of the data, radio data, or
yeah, or potential
data?
Utilizing the Eclipse monitors and other aspects.
Well, so I've got an answer to that, because it has sparked my interest in this. Any data set, almost any data set, the value of that is it requires that you ask more questions. It will generate more questions, way more questions than it will answer. And so when you look at your data, I like the comment that, well, this was wasted data. And I would say, no, it's not wasted data. It's data, and it's maybe useful to you or not useful to you, but it's data. And you may think it's wrong. Well, then why is it wrong? Why is it? You know, you turned it on inside. Well, I think that's a good calibration. Was it 72 degrees inside? Do you see it change as you go outside? So any data set, if you take it seriously, will generate many, many, many more questions. And that's for me, the pleasure of this kind of stuff, is that you think it's going to be easy. You think, oh, I'm just going to watch it go up and go down or whatever. And then you see a little blip. Then you got to decide, where did that blip come from? And maybe it's a solar flare. Maybe it's just the way that sensor works. And so how do you figure that out? What do you do to rule out, that student came up with 2 hypotheses that were really interesting, but I'll bet you can come up with 50 hypotheses of why there was a data blip. And then you just figure them all out. You sort them and you say, okay, I've eliminated that. Anyway, I think once you get a data set, the pleasure of it is almost not the data itself. It's what questions that you can generate by thinking about the data that you're looking at.
Yeah, I really want to second that and say, from, I've been doing scientific observations and analyzing data and working with science data for 30-something years. And the fun part is always in the surprises and in the new questions, right? You come up with a new way to measure something, you have ideas, this is what I'm going to measure, this is why I'm measuring it, this is the question I'm trying to answer. And if you get all of that and it even works, that's actually not as much fun as if you do the measurement and say, boy, Jupiter didn't look anything like we thought it was going to look. And now we have 50 new questions, and we have to figure out how to use our data a different way to understand it. And we have to tell all the theorists who had theories, you got to start over because all those theories are wrong. That's the fun part. And lots of times, there's been Nobel Prizes won from people looking at data and saying, I see noise in this data that I didn't expect. So there's a lot of value there. And the follow-up now, where we continue and we say, let's work together, let's try to look at all this data set, generate new data sets, and find the puzzles and solve them. That's the fun stuff coming up.
I agree.
I got one more thing to add. I was just telling somebody or some students this before. There's a professor at MIT or a grad student at MIT. He was trying to figure out how fast a motor was turning, and this is in the 30s, and you don't want to put anything on the motor because then it'll change the speed of the motor. He's trying to figure out how fast the motor is turning. So he needed to figure out exactly how fast it was turning. So he thought, well, you know what? If I could blink my eyes, and put a mark on it, and if I know how fast I'm blinking my eyes, and if the mark doesn't move, I can kind of figure it out. And so he had to go invent this light that flashes so that he could watch the vary the speed of the light flashing and watch the motor turn. He invented stroboscopes. His name is Doc Edgerton. He's a real hero at MIT. But him inventing the stroboscope, and I'm sure you've seen all the pictures of the bullet that goes through the apple and all that stuff. That was a byproduct. That was something he had to invent just to figure out what he really wanted to know, which was how fast the motor was turning. Once you start asking questions, boom, wild things can happen, and that's the fun part of the ride.
Yeah, it is always important to do it yourself, be a part of it. That's also important. You know, I mean, everybody, as Steve mentioned, science is sort of grown in a way. It is more and more teamwork. You know, I mean, it's national, international. No country can do big projects. It has to be. So any little thing always adds to the big thing, right? So, and I'm very impressed by your enthusiasm. That is the most key driver. You know? And so I really enjoyed listening to your experiments, and you know, look forward to not quite some time for the next total eclipse, but there are other opportunities to participate, and covered program is another one of the opportunities. And if anyone has interest in sun, you know, space weather, this is the place.
I think I know we have time constraints, but we do have a couple more questions. If any of our panelists, if we can hang on, I know Velu, you might have an.
Yeah, I'm just leaving actually.
That's okay. That's okay. If anybody else can hang on, we have just a couple more questions that we'll field, and then we'll cut the broadcast. But we have follow up because we just go to webinar, so we'll be able to follow up with you.
Dan, I think this might
Thank you so much, Lisa, for.
Bye, Velu.
Dr. Velu.
Bye. Later, Velu.
Bye.
What does the eclipse look like from space?
Oh, only one of us can answer that.
Yep.
Well, none of us can answer that because I wasn't there I wasn't in space for an eclipse. I saw a picture. I was hoping the station would take a picture during the eclipse. I saw a picture online. I think it was fake. I don't think it was a real picture. So, but you know, what you can imagine, so if you're in low Earth orbit, ironically, what you want is cloud cover. I mean, you want cloud cover because now that gives you a nice white sheet to see what the shadow looks like. If it's on the ground, it's probably harder to see it. And so, but you know, I would imagine it's going to look like what you think it looks like, which is a black spot. It won't be sharp. It will have penumbra around it. So it'll be a black disc, a black spot. What I think would really be interesting is to watch it move, you know, with some velocity. But we're traveling pretty quickly also, so I don't know how much time you would have to watch it move. But so I suspect that the ISS was not in the right position during a totality to get a picture of it. There might be weather satellites that have images, but I haven't seen that either. The only thing I saw online afterwards was, I think, obviously a fake. So, but you can, I think you can imagine what it would look like, and it would look like that.
Right. If I could share my screen for a minute, I can show you what an eclipse looks like from space, not on Earth, but an eclipse at Jupiter.
Oh.
I don't have to figure out how to share my screen on GoToMeeting if I can. Brian, is there a way to do that?
I'm getting
How about we circulate that image?
Yeah, we'll send it. We'll send it because we're gonna send a.
You can find it just by Googling it. Google JunoCam IO shadow, and there are images out there. The Juno spacecraft camera took pictures of Jupiter when the shadow from Jupiter's moon Io was going across, and it looks a whole lot like what Dan just described.
I'd like to offer that there was an amateur radio contact during the eclipse with the space station talking to an astronaut. The angle that they were in orbit, though, did not give a good, clear image over Utah. So the ARIS contact, they were able to talk about it. So they also projected if they could see it clear, that it would be a little fuzzy. So that was one verbal observation I heard of.
That's cool. Okay.
All right, one last question.
One last question.
A very Gabbard specific question. Can we use the Gabbard telescope to measure radio waves at 1.42 gigahertz?
I understand why they're asking that question. That's a really important frequency. And the answer is not really. So the radio telescope can handle it in terms of the telescope itself. The receiver system, there's parts of it that can handle it and parts that where we'd have to take out some filters and things. And then the big kicker there is there's a lot of radio interference at the low frequencies like that. And 1.4 gigahertz itself won't have a lot of interference, but there'll be radio signals from other things that are too close to that to work very well with our particular radio telescope in the location it's at. I don't know if Ryan, if you want to add anything to that, because you've got more detailed knowledge than I do about which filters you have to remove.
Yeah, DSS 28, we have a physical limitation down to 3.1 gigahertz. So that's the lower limit that we can get. And then at DSS 13, we're currently at 2.28 gigahertz with a 40 megahertz wide bandpass filter. So those are our two limitations for getting down to that line at 1.42.
So 1.4 gigahertz for people who don't know is frequency of a hydrogen line that's really important for doing astronomy, and has also been suggested as a great frequency to look for signals of extraterrestrial intelligence, because people might use it as a marker to try to send us a radio signal. And we do have a SETI campaign for Gabbard, but not at 1.4 gigahertz.
Mm-hmm.
All right, one more question. Did anyone test or see evidence of electrical grid impacts due to the sudden reduction in solar power?
Great question. I got no idea. Anybody? But
yeah,
I'd love to follow up on that.
There's a lot of data out there, because I would, with people with solar panels on their roofs, you might even be able to predict where their house is based on their output, because you can see how long what the occlusion was. And anyway, there's a lot of homegrown data out there that might be used to make a map of totality based on solar output, the output of your solar panels in your house.
That's interesting. Oh, wait.
Yeah.
I was gonna say they didn't get anything that had the direct influence of the sun and solar panels, but I did see things that were sensitive to light levels. They did go off, and they were reacting to when going down.
Cool.
That is great. I just have thoroughly enjoyed this evening. I just want to thank all of our amazing panelists. It's really been the whole ride, like Bob was saying earlier, it's just been a tremendous opportunity. I've just loved seeing our students collaborate. I loved how they shared notes and little gifts and ducks and monitors and data. I really absolutely loved watching you all mentor our students and seeing them just really just blossom and think about data in new ways and really feel so empowered. And really just being able to put all our tools together, whether it's our, radio antenna or a tiny Eclipse monitors, or just their feeling, right? What they saw and what they felt during the experience. So thank you. Thank you to everybody who's been involved. It wouldn't have been possible without everybody who's been a panelist tonight, and also people behind the scenes who helped us plan this whole way. So let me recognize them as well. So Ryan Dorsey, Gisela Corona, Nancy Cruiser Jenkins, Erica Pagano, Sandy Marshall, Judy York, and Margaret Baggio. Thank you so much for all the work that you've put in. It's been really a fun ride. We are, like as we've said, looking forward to more opportunities to bring our community together, our international community together, to do science and engage in real learning. That is at the heart of everything that we do at Gabbert. Also, we are going to send a few things as follow-up. One of them is a survey. As a NASA grantee, there's data that we need to provide to NASA so that we can keep doing things like this. So we'd really appreciate it if you filled that out. And we're also going to share additional information on how you can get involved in all of these projects, whether it's NASA Seas or Gabbert or any of the other things we've talked about. So with that, we're about 37 minutes over our projected time, but it was fun. And when you're having fun, why quit? So it's time to sign off. So here from Gabbert headquarters in Apple Valley, California, we wish you a good night and talk to you soon. So thank you, everybody.
Thank you. Thanks, Lisa.
Bye.
Bye.
Very
Bye.
good.